the president of the Institute for Humane Education, which is in Surrey, and I'm also steward here at the Good Life Center. And I was really excited to help this summer with organizing with Warren and Bob and Doris the speaker series. And there are a few people who I really, really wanted to bring to the Good Life Center, and one of them was Dr. Habib Dagher, who's standing next to me right now. And the reason I wanted to bring him was because he and I spoke at the first TEDx Dirigo event, and I was completely riveted to his talk. I thought it was the best talk that I heard that day, and have been trying to follow his work ever since, and really wanted our community to have the opportunity to hear him. So that's my story about Dr. Dagher, and now I'm going to read his actual bio, which I don't understand completely, but I'm going to read it anyway, and I hope I can pronounce everything properly. Dr. Habib Dagher, the founding director of the University of Maine's Advanced Structures and Composites Center, is a world-leading advocate for developing advanced structural systems which simultaneously optimize structures, materials, and construction. Under his leadership, the University of Maine Composite Center has gained national and international reputation for major research and development projects, such as the first grid-connected floating offshore wind turbine in the U.S. and the first in the world made out of concrete and composite materials, the inflatable composite arch bridges, bridge-in-a-backpack technology, the first modular ballistic protection system to protect troops in tents from blast and ballistic threats, development of coated wood technology for blast and hurricane-resistant wood buildings, and the longest carbon fiber composite vessel built for the U.S. Navy. Are you with me?
I am.
That is so amazing. So Dr. Dagher has received numerous awards for his work, including the Carnegie Foundation Maine Professor of the Year, the New England Board of Higher Education Excellence Award, the University of Maine's Distinguished Maine Professor Award, and the University of Maine Presidential and Creative Achievement Award. So please welcome Dr. Habib.
Thank you. Thank you. Great to be here.
Just a couple more announcements.
Okay. Please.
So a couple things to tell you is so Greg, where's Holly? Here she is. So Greg and Holly are the stewards here this summer at the Good Life Center, and they've made some popcorn and tea, which you are welcome to enjoy after the talk, and also to talk to Dr. Dagher a little bit. And there's also an art show behind me if you want to take a gander at that. And next week we have our last speaker in the summer speaker series, Dr. Greg Creech, also somebody who I'm excited to know and bring to our community, and he's coming from Vermont to talk about the art of taking action. He's an amazing speaker, an amazing person, and I hope you'll come out for that. Okay.
Great, thank you. Appreciate the opportunity to be here with all of you. Would you mind just taking a minute to walk around the room just to understand what business you're in or what you're interested in, just who you are here?
Yeah, no business, just getting in trouble. Warren Berkowitz, a retired educator and a manager of the Good Life Center.
Great, thank you.
I'm an aide to a disabled person.
Great, thank you.
I'm David Dietrich, live in Blue Hill, run a little wastewater treatment plant.
Wonderful, thank you.
I'm Rick Decker, I live in Brooklyn, and I'm a retired meteorologist.
Oh, wonderful, thank you.
I'm Mike Wooden, retired teacher.
Wonderful.
I'm Doug Callan, a retired doc, and really interested in alternative energy sources, and been following kind of what's been going on in Maine around wind power.
Great, thank you.
And I'm Posey Callan, and I care a lot about women's rights and equal rights.
Excellent.
Working on that.
Wonderful.
I'm Nancy Dewey, and I'm a beekeeper and a gardener and a rug breeder.
Excellent, nice to have you here.
My name is David Rosa. I'm a reporter with the Ellsworth American.
I didn't hear what you said, I'm sorry.
I'm a reporter with the Ellsworth American.
Oh, great, nice to have you. Yeah, thank you. Nice to have you, yeah.
I already introduced myself.
I'm Edwin Bartol, a veterinarian.
Wonderful, thank you.
Richard Martin, 58 years in earth construction with HE7.
All right, yeah, absolutely. All right. Excellent, good to have you.
Dick Greger, I'm a mechanical engineer.
Wonderful, Thank you. Yes.
David Zackham, I live here on Cape Rosie.
Great. Thank you.
Greg Benson, one of the resident stewards here at the Good Life Center.
Great.
Holly Peterholm, also a resident steward.
Great.
Chris Cox, retired boat builder, fisherman, and now minimalist.
All right.
I'm just traveling through Maine right now and working at the fund.
Great.
Bob Jones, gardener.
Wonderful. Thank you.
Jody Spear, art history editor, but now working as an environmentalist with a focus on toxics.
Wonderful. Well, it's such a great pleasure to meet all of you today. And just a bit about personally who I am. I've been at the University of Maine as a professor for 30 years. I have 4 children, 3 daughters, who also are very interested in women issues, and then I have 1 son as well. The 3 daughters are all going to UMaine, have gone to UMaine, are going to UMaine right now, and my son is at Bangor High. I've been a professor for 30 years at UMaine. Came in as a structural engineer, got my degrees in Ohio and Wisconsin. My wife's from Wisconsin, Madison, and we've been here for 30 years together. We didn't think we'd be here for 30 years, but we are. So it's a great place to be. And I'll tell you a bit today about the offshore wind opportunity, but more about also what we're doing for research at the University of Maine to see why we're doing what we're doing and why we got where we are today. So what is deepwater offshore wind? Deepwater offshore wind is basically offshore wind that blows over water that are very deep up in the ocean. As you know, we have very deep waters off the coast of Maine. If you're about a mile off the coast of Maine, you're in 300 feet of water. We have very deep waters. If what you're looking here at right now is a floating wind turbine. This floats over the water and harnesses the very strong winds that blow over the water. The offshore wind resource in the Gulf of Maine is big. We have a very large offshore wind resource. It's 156 gigawatts of offshore wind. Can you hear me in the back all right? Oh, a gigawatt is roughly, you can't hear me out there? There's a spot up here if you'd prefer to come up.
I don't think we need the fan unless...
Yeah, we can turn the fan off.
I'll get it. Okay. I'll get it.
Okay. Yeah, it's good. It's 2 birds with 1 stone, huh? Is this better? Can you hear me better now? Excellent. Within 50 miles of the coast of Maine, there's 156 gigawatts of offshore wind. There's a gigawatt is roughly a nuclear power size, good sized nuclear power plant. Okay. So we have 156 nuclear power plants worth of wind blowing off of our coast. And right now we're not doing anything about it. Okay. And so about 10 years ago, we've started a research program to figure out how to bring this energy both ecologically and cost effectively back home. And that's what I'll talk about today. And I work at the Research Center at the University of Maine. Please have a seat. Just got started, so you get at the same time. Would you mind introducing yourself? Everybody else did? Yeah. Just tell us who you are, what business you're in. Or?
Oh, I'm Carolyn Waite, and I work for the Good Life Center.
Excellent.
I'm Parker Waite, Carolyn's husband.
That's a good way to get introduced. Nice to have both of you here. Yeah. So it's a big resource for the state of Maine. How do we find a way to harness it? So I'll tell you a bit about the University of Maine Advanced Structures and Composites Center. Can you see the screen here? Yep. I'll see if I can move it back a little bit. Yeah. Usually I break something when I do this. So. All right. All right, right. We're okay now. Can you see better now? Yeah, okay. So I'll talk about the University of Maine Composite Center, what we do. We're in Orono, Maine, at the University of Maine. And then I'll talk about offshore wind and where we're heading with it in the state of Maine. This is the center where I work. We founded that in 1996. There were 4 of us faculty who founded the Research Center. It's at the University of Maine campus in Orono. As you know, the campus was established back in 1865 as part of the Land Grant Act of 1865. And we're the largest university in the state of Maine. We have about 12,000 students. We've been the first graduate at the University of Maine, the first class, was a civil engineer. graduated right after the opening in 1865. So engineering goes a long ways at the University of Maine. Actually, the engineer who was in charge of the Hoover Dam, who built the Hoover Dam construction, was a UMaine grad as well. His name was Francis Crowe, and he was a person with very few words. When the president asked him to come up to the podium and introduce the Hoover Dam, he said a few things, but to the gist that Mr. President, distinguished guests, here it is. What else could I tell you? So the university goes a long ways in engineering, and this research center we built starting back in 1996, and we started with 4 faculty, and today we have 180 people who work there. There was no lab there. Now we have a 100,000 square foot facility. It's the largest research center at any university in the state of Maine. And we work on bringing advanced materials into construction. How do I build it with a smaller environmental footprint? How do I build it faster? How do I reduce the cost? This is what we work on. That's what our expertise is. So we have a number of structural engineers, mechanical engineers, civil engineers, material scientists, and that work together to solve problems that society has. Since we got started, one thing I'm most proud of, we financially sponsored over 2,000 students that have graduated from our laboratory that are now all over the world and Maine and in the US working. And the way students typically work in the lab is they come, if you're an undergrad, you can work up to 30 hours a week, and you get paid to work on a research project. And the project's typically sponsored, financed by somebody who wants answers. It could be a private company, it could be a federal government, federal agency, and so forth. So we compete for research projects all over the world. And then when we bring the money into UMaine, we hire the students to work on these projects. So the students get to have some very exciting opportunities to work on projects. These are our partners across the country and the world. So we have over 500 partners and clients that send their money to Orono to do research and development, or partner with us on research projects. These are examples of projects we've worked on over the years, just to give you a sense of what we do. This happens to be a boat built for the US Navy SEALs. There's a company in Maine called Hodgson Yachts in Boothbay Harbor. Have everybody seen that? Yeah, they've been here for a number of generations, and they used to build wooden boats, but we partner with them on building a boat for the Navy SEALs. The Navy SEALs have a boat called the Mark V. It's made out of aluminum, and when you go in at 50 knots, which is what this boat's supposed to do, and you have 4 or 5 foot waves, the wave slamming forces on the hull were causing 10 to 20 Gs of shock loading, 10 to 20 times the acceleration of gravity. So the SEALs were getting shattered molars, they were getting damaged bones. So we redesigned the hull using a shock absorbing composite. It's got a sandwich structure with carbon fiber on both sides and Kevlar, and it absorbs the impact of the waves in the hull and transmits less of it to the occupants of the boats. So Hodgson Yachts spun off a business called Hodgson Defense Composite, hired 30 people to build this boat for the Navy SEALs. And that's examples of things we get to work on. This is our lab from an aerial view, and this is the wind blade coming into the lab. It's 56 meters long, so over 160 feet long. And it came from all the way from Arizona to be tested in our laboratory. And I'll show you what it looks like. And you can see the size of that when you look at the cars on the side. So this is what the lab looks like on the inside, the part of our lab, the offshore wind lab in this case. Here's a blade being tested, mounted to this big wall. But this blade is 160 feet long, roughly. That's like a 16-story building. And what we do is we test these blades in our lab to make sure they work before we put them out there. And we subject them to what we call static loads and fatigue loads. Fatigue loads when you move it, bend it back and forth, to make sure it's going to hold up 25 years out there. So we use computers and actuators to do this work. And this is a view of the blade, and you can see here, it was shot a couple of weeks ago here in the lab. And that's a 160-foot long blade doing this, right, to do it moving the way it is. Let me see if I could run it again. So you see those yellow masses moving back and forth? That's all it takes to move the blade. And then every time you move the blade, you put enough stress on it, which is one of the worst stresses it'll see during its lifetime, and you do this over and over again for a few months. And that's equivalent to 25 years of wear and tear out there in the real world. That's examples of how we do this kind of work. Here's another shot where the blade's being bent the other direction. It's called in the flapwise mode. In the other video, it was bent in the edgewise mode. Just to show you a sense, this is again This blade is 160 feet long. It's moving at the tip 30 feet. Okay, and you do that for a couple of months at a time. So, and that's how you make sure the blade really works. It's going to hold up in the world out there. And so companies from across the world send us our blades and send us technologies to prove them out, and we certify them so they will sell them out there in the real world. So.
What kind of failures have you seen in those tests?
So far, we typically do not break the blades. We put them through fatigue loading to see if they're going to hold up, and so far so good. We haven't seen any major issues. This blade will be the first one we're going to break after we test it. So we're going to put 50 or 25 years of fatigue on it, and after that we're going to look how much strength is left after 25 years. So we're going to break this blade. And when you break it, the tip of it will move about 50 feet to one side. So that's how much it'll break. So it's a very interesting test. Another part of what we built recently a wave wind basin to test ocean energy. When we say ocean energy, we're talking about wind energy, offshore wind, which we just discussed. Wave energy devices or tidal energy devices are examples of things we could test in this laboratory. This facility creates waves and creates winds to replicate different environments across the world. And you can have winds and waves come from different directions. It's an ocean engineering lab. The reason I'm very pleased about we're able to put this together, we've worked for 5 years to assemble this new addition to the lab, is there are no facilities in the US that combine wave and wind testing. There are wave basins in the US, there are wind tunnels in the US to test airplanes, but nobody's put a wind tunnel over a wave basin yet, and we're the first to do that. And that allows us to test all kinds of very interesting conditions. So we can, typically we test structures at the 150 scale. So you take something real and shrink it by a factor of 50, and then you have to do the physics right to make sure it performs like the big one will. And that's really what it is. This is a really big physics experiment in the lab. And the floor or the basin moves up and down, so you can actually change water depth, because you can test things under different water conditions or depth conditions. This is the wind machine at the very end. So the wind machine can be moved to different locations to create winds of different sizes. You can see the size of the facility here. But what can we test in there? Not just offshore wind, but we can test, we're looking at testing ways to grow fish out in the deep water. So this is fish holding tanks, that have to survive extreme winds and waves and so forth. So how do you know it's going to survive when you build it? So you can design it and test it in a facility like this. As you know, one things we need to do is to figure out how to feed the world, but we can't grow all the fish. We can't fish as we've always done because of the depletion of the fish stock. So can we build deep water aquaculture facilities to help feed the world essentially in the future? And that's the kinds of conditions, the kind of facility we could use to test these structures. We can test ship structures. As you know, we're all concerned about global climate change, and there's a number of cities across the east coast of the U.S. right now and others trying to figure out how to deal with it and how to plan for these sea level rises that we're going to be seeing in extreme storms. So in a facility like this, you can actually design dike systems and other systems and build a model of the city and then put it in there and test it and see how it's going to work out. So these are things you could do in a facility like this. Here's what it looks like. This is we're just applying wind right now. This is a wind machine right over here. So we can test up to 240 miles per hour equivalent in the real world. Of course, we don't apply it to 140 miles per hour inside, but that's the wind machine being turned on right now. And the machine allows us to change water depth, wind speed with height, just like it does offshore. And this is just the wind blowing over the water. We don't have any waves applied, but I'll show you the waves in just a minute. This is the depth of the facility. You can see how deep the unit is with people working inside. That's the wave equipment. Essentially, they're wave actuators, that big paddles that move back and forth. And you can use that to create almost any wave environment you'd like. And this is what the waves look like in the inside the facility. And that's the wind machine. There you see the wind tunnel. So by creating waves from different directions and different heights, you can model almost any ocean environment to prove that the technology really works. And you can see here the wave machines moving back and forth, and they're numbered 1 to 16. We have 16 of these actuators controlled by computers that would allow us to create waves and wind conditions that mimic almost anything you can encounter in the real world out there. So you can see here in slow motion what it does, and that's the wind machine. Of course, there's 3 people out there, one of them being myself, in the wind machine, but it's not turned on right now. It gives you a sense of the things. Here's how the wave paddles or actuators work. They can work all at the same time, or they can move differently depending on how you control them to create different sea states. Okay. So that being said, here's a 150 scale version of a 6 megawatt floating turbine that we tested in our laboratory. And this is being put in under a 500-year storm. So relative to the size of this unit, there's a 500-year storm right now of waves going at it. To give you a sense of size, does any one of you know what a 500-year storm, in terms of what wave height that is in the Gulf of Maine? If you're 20 miles offshore and you get hit by a 500-year storm, that's about a 70-foot maximum wave height. Okay, if you're a meteorologist, you know that's not that you get a lot. You don't get every waves. They're not going to be 70 feet. You're going to have waves of different heights that come in at you. But the maximum wave for a 500-year storm is about 70 feet. And these units, that's a 150 scale. So how do you test the 150 scale? What you do is you shrink the wave height, and then wave height happens to shrink linearly. With scale, with geometric scale. So if you take a 70 feet, divide by 50, that's 1 1/4 foot. So if you apply a 1 1/4 foot wave on this unit, you'll get essentially an equivalent 50-year storm. Yes.
What's the maximum height waves that you're aware of?
In the Gulf of Maine? Yeah, we worldwide, I think I don't know what worldwide is, what the maximum wave is altogether, but in the Gulf of Maine, we've never seen a 500-year wave. We haven't seen 70-foot waves yet, at least measured them, okay, that I know of. So, yeah, so these are very, very extreme waves, very, very unusual waves. And when you try to predict 500 years, we haven't been measuring waves for 500 years, so we don't really know. We don't have records that go that far, that go that far back. But that's certainly a 70-foot wave is the kind of things that we typically design for, and those are predicted. Not real wave. What you do is you collect data over a certain number of years and use statistics and probability to predict what a 500-year wave might look like. So those are what we call calculated waves, not measured waves, because we haven't seen them out there. But we've calculated or predicted what could happen. We use distribution called extreme type 1 distribution, for example. If you're familiar with statistics, that's what we typically use to predict what happens in a 500-year type event. A 500-year wave isn't a wave that comes in every 500 years. It's a wave that has a probability of 1 over 500 of being exceeded in any 1 year. Because that's the definition of 500-year wave. So let's talk about the state of Maine. A lot of us like to rely on ourselves in Maine in our own homes and put in solar panels or small wind turbines. But can we do that at the scale of the state? Can we do that at the scale of the region? Can we do that at the scale of the country? These are the kinds of questions that we're trying to answer right now. Let's talk about a Maine family. You all remember in 2008 when we were paying $4 a gallon for gasoline, right? Okay, how many of you believe we're not going to go back to $4 a gallon? Okay, all right, so I think we're all on the same page here today. So when we were at $4 a gallon, the average family in Maine paid about $10,000 a year in energy costs. Okay, if you look at your own family and think about your own family in Maine, and the problem is not electricity for the Maine family. About $1,000 a year is the average family electricity bill in the state of Maine. $4,000 a year is the heating oil, because most of us use heating oil to heat our home. 70% of Maine roughly uses heating oil, and to fill the tank in the basement, it's about $4,000 for the average family. And then gasoline. The average family in Maine has 2 cars. Being a rural state, we travel a lot, with long distances to go to work. And the average family that has 2 cars spends about $5,000 a year to fill the tank on the 2 cars. This is at $4 a gallon, of course. At $2 a gallon, now you can cut these numbers in half. So on the average, it's about $10,000 a year. And the average family income in Maine is $45,000 to $50,000. So you take 10, divide by 45 to 50, you're looking at about 20% plus of the family income is going to energy. And when you put that in perspective, you ask yourself, what are the taxes in the state of Maine? Right, that's more than the state taxes that we pay, isn't it? Okay, $10,000 a year. So it's a big issue. And what control do we have on that right now? What control do we have on the cost of gasoline? What control do we have on the cost of heating oil? Zero. Okay. When we're out in Augusta and trying to cut taxes, and I'm all for cutting taxes, but if we're going to go out there and cut taxes in Augusta, that's what we're talking about, cutting taxes 5% maybe or so. But when you look at a number of $10,000 a year that leaves the state of Maine in energy costs, that's more than all the taxes that we pay. And we should be paying attention to those kinds of numbers because they really affect every family's life. So you put that all together for the whole state of Maine, how much fuel money leaves Maine every year? That's about $6 billion leave the state of Maine in the form of paying for heating oil, paying for gasoline, and paying for natural gas and other forms of fossil fuels. As you know, we don't mine fossil fuels in Maine. Okay, so everything other than of course wood that we burn, but we don't buy fossil fuels. But we pay about $6 billion a year that leaves the state of Maine in fossil fuel prices. Another question for all of you: what is the annual state budget in the state of Maine? Do you know what we have to spend every year on all of our budget in Maine? $3 billion. So that's twice the annual state budget that we pay for everything: education, healthcare, cars, roads, bridges, whatever. That's twice that. And we have no control over that today. None. Though this price, $6 billion a year, to give you a sense, for every dollar per gallon, for every dollars per gallon that gasoline goes up and then heating oil goes up, another $1 billion leaves the state of Maine. Okay. Now, when you're out there in Augusta trying to figure out how to cut taxes by 5%, which is great, it's a great thing to do, we're really missing the boat. This is a big piece that we need to focus on. How do we reduce those costs? Now, I haven't talked about the impact of burning fossil fuels on the environment. Of course, we all know what it is today, and we're not going to belabor that. But it's a big deal, and Maine today puts out per capita, we're one of the top carbon polluters in the United States per capita. Okay, that's a big deal. One of the top carbon polluters. Okay, so it's another thing to think about as we start thinking about new evidence. It's basically manufacturing facilities burning a lot of heating oil. That puts a lot of CO2 up in the air and other poisonous gases in the atmosphere. So if we can stop burning oil, for example, heating oil, it cuts into it quite a bit. And if we use less heating oil to run some of our manufacturing facilities, that would also help quite a bit. So how much electricity do we use in Maine? We use about 2.4 gigawatts of electricity per year. That's, well, it's not per year, it's 2.4 gigawatts of capacity. So what does that mean? It's about 2 nuclear power plants. A good-sized nuclear power plant is 1 gigawatt. Okay, 1 gigawatt is 1,000 megawatts. A megawatt is 1,000 kilowatts. That's basically what we're talking about. 2.4 gigs is what it takes to power the whole state of Maine. And how much did we say we have for offshore wind? 156 gigawatts sit off of our coast. So if you look at that resource, it's a huge resource. It's an absolutely huge resource. We just haven't taken the time to figure out how to bring it home cost effectively. And that's really the purpose of our program. How do we bring this energy cost effectively back home so we can use it without subsidies? That's really what we're hoping to do, so we can be cost effective without subsidies. And that's not a simple goal. It's not an easy goal. But if you don't start somewhere, you don't get anywhere, right? So that's what we're trying to do. We're trying to get at that problem. So let's talk about the offshore wind. How much offshore wind capacity does the U.S. have as a whole? This is an offshore wind color-coded map of the U.S. showing off the coasts where the wind blows hard or doesn't blow hard. How good is it? How is it not? And then the areas in orange and red are the best. And then green is not very good. Yellow is really poor. So as you go from yellow to green to red and orange, that's really when it gets really good. So if you travel on the East Coast from Florida to Maine, what happens? The wind gets better and better and better. And if you look at the Northeast U.S. as a whole, the Northeast U.S. has the best offshore wind resource in the United States, on the East Coast of the United States. Then if you look on the West Coast, you've got a lot of good wind right over here, but not a lot of people. Okay, and then you go to California. Of course, you have a lot of people. But in the Bay Area right here, the wind is really poor. You see how yellow it is? Yeah. The reason it's poor is because the jet stream runs north-south, and then it has to go over land before it gets back to the water. So you get a really poor wind conditions there. But if you get north of this area, you have some really good wind right here off the LA coast. But if you look at where it makes sense to use offshore wind in the U.S., the Northeast makes a lot of sense. Why? Because we have lots of wind. excellent wind resource. We pay the highest electricity costs in North America, the Northeast U.S. does. And then we have the largest population concentration. Okay. Now, if you look at the area from New York to Maine, drawn in blue right here, that area right there, that area has close to 55 million people. Okay, that live in an area no bigger than the state of Texas. Actually, this area in blue is less than the size of Texas. So we're like a big state for all the way from New York, Pennsylvania to Maine that have a great offshore wind resource. Lots of people live in it, and so there's a good opportunity, good reason for all of us to work together to figure out how to bring this resource cost effectively back home.
That's a 90-meter wind table?
Yes, that's 90 meters. Yeah, that's 90 meters above the water. Yeah.
What's the height of the turbine?
About 100. So this is so the wind speed would be better than that at hub height. Yeah. Yep. Thank you.
What is that capacity number mean?
Where is that?
Measurable? Is that,
Oh, gigawatts? Gigawatt is a...
what hours,
yeah.
years? What is
Yeah, yeah. This is gigawatt, which is called, it's a name, that's how much offshore wind capacity there is, how much power you could harvest. A watt is a...
Power.
Yeah, it's a unit of power, just like when you have a 100-watt bulb.
Yes.
When you say I have a 100-watt bulb, it's not how much energy it uses, but how much power it produces. So the power that you have offshore is 4,000 gigawatts. So to put that in perspective,
yield per year,
yeah,
given its intermittency.
yeah, good point. I'll get to that in just a minute. A gigawatt, as we said, is roughly a nuclear power plant. Okay, so as you know, we all know, it is no secret to anyone here, the wind doesn't blow all the time, it blows sometime of the year. We ran some numbers, what we call capacity factors. What's the capacity factors? Net capacity factors. Capacity factors is what's the average you can produce every year compared to the nameplate capacity of the turbine. Okay, the capacity factor offshore, off the Gulf of Maine, off Monhegan Island, is about 50%. The gross capacity factor. And that's because we have such steady winds. So on land, the capacity factor will range from 20 to 30, 35%. Offshore, the capacity factor goes up quite a bit. Why? Because the wind is steadier offshore and there's less obstructions to the wind. We have much better wind regimes further offshore than we have near land. Now, to put that in perspective, for those of you who think of hydropower, for example, okay, well, do you think hydropower plants produce the same capacity year-round? No, they don't, because what happens, you know, the rivers can have lots of water for parts of the year and very little water the other parts of the year. So when there's lots of water flowing through the river, you get closer and closer to the capacity of the nameplate capacity of the water turbines. Okay, let's look at the Hoover Dam. Does anybody know what's the capacity of the Hoover Dam? Actually, yeah, the full nameplate capacity of the Hoover Dam is 2,000 megawatts, 2 gigawatts. So the Hoover Dam is a 2 gigawatt dam. Okay, what's its capacity factor? Does it produce 2 gigawatt throughout the whole year? No, it doesn't. It's 25%. So the Hoover Dam only produces 25% of its nameplate capacity. So the reason I'm saying that here is offshore wind in Maine produces 50% of its nameplate capacity, a heck of a lot better than Hoover Dam. So that's a wonderful resource that we have out there. Great resource. So now how do we bring it home cost effectively is a challenge. That's what we're trying to work on. And in the Gulf of Maine, as we said, northeast U.S. we have 55 million people. In the Gulf of Maine, we have 156 gigawatts of offshore wind. Okay. Now, in the U.S., we have 4,000 gigawatts. Why am I saying that? Because that's important to put that in perspective. Within 50 miles of the U.S. coast, there's 4,000 gigawatts of offshore wind, about 4,000 nuclear power plants worth of wind when the wind's blowing. It's full capacity. Okay, what does that mean? What does it take to power the whole U.S.? It's a good number to remember. It's very easy, actually, to remember. It's about 1,000 gigawatts. Okay, it takes about 1,000 gigawatts to power the whole United States. And how much offshore wind capacity does the U.S. have? 4,000 gigawatts. Now, that doesn't mean we're going to power the whole United States on a wind. I'm just out of offshore wind. Nobody wants to do that by any stretch of the imagination. But what we're saying is, it's a large resource. It's an important resource. We need to figure out how to bring it home cost effectively. That's what we're talking about. And what the energy future will be a mix of resources, that being one important part of them that we can bring into the future. The other thing that's really important about offshore wind is that the resource is very close to large cities. Okay, New York, Boston. Where are these cities? They're on the water. We have major population concentrations near the water. The majority of the U.S. lives actually in the coastal states in terms of population. So if we develop the offshore wind resource, we can actually power a lot of the coastal states with very short transmission lines. Okay? Rather than build wind farms in the Midwest from North Dakota to Texas where the wind's really good on land and build transmission lines across country, you can actually build the offshore farms closer to the cities, 20 miles off the cities. Now if you build them 20 miles off the cities, then because of the curvature of the earth, you're not going to see them. Okay? So if you're about 20 miles offshore, then you're not going to see these turbines anymore because of the curvature of the earth. Because, you know, when a boat sails into the horizon, you don't see the boat anymore. Again, the turbines, when it's 20 miles offshore, you're not going to see it. And that's, if we're building floating turbines, we can place them over 20 miles offshore so nobody can see them from land or hear them. Moving on, we put together a plan starting back actually in 2006 and 7, but these are the highlights of the plan. And this is the plan UMaine put together, working with industry, working with state agencies. And the plan is to we started by figuring out what's the best technology to drive costs out of offshore wind, and we determined it's the floating technologies. That's the best thing we could use in our environment. We determined it's made out of concrete. That's where we'd like to go, and we started actually by testing back in 2011 150 scale versions of our floating turbine designs to see what works the best. And then in 2013, we deployed a 1:8 scale version of the 6 megawatt machine off the coast of Castine and kept it there for a year and a half, again to collect data. And just about a few months ago in May, we got really good news from the Department of Energy that they've selected our project in Maine as a major national project. They're going to invest $43.7 million into it to help us build 2 turbines off the coast of Maine to test them, to see how they work out. So, and that was a big deal because the program started with dozens of projects, and now they're down to 3. We're one of the 3 that are left. And each one of the 3 would get that kind of money to move it forward. Of course, we're going to need more money from the private sector to get there, but this is a very good chunk to start with. Our goal is to start in 2017 constructing 2 6 megawatt turbines that we'll be placing as a test off the coast of Maine, off Monhegan Island, and to test the technology. And in the future, once the technology is proven and we can get financing for the projects, to build more farms over 20 miles offshore, not only in Maine, but of course throughout the U.S. and the Northeast in the United States. So that's the plan. So let's talk about technology now a bit. So what we have a technology called Volturnus. It's a floating wind turbine technology that can reduce hull costs compared to others by a factor of 50, by a factor of 2, by 50%. And the technology we have uses floating concrete hulls using technology used to build concrete bridges. Now, if you go up and down the coast and you look at the long bridges built over waters, what do we build them out of? Concrete, pre-stressed concrete. Why? Because it doesn't corrode as often as steel. Steel corrodes in the water. So people use concrete, and we've been building these concrete bridges for over 40 years in the United States, using what we call pre-stressed concrete. That's the concrete that's squeezed together to keep it from cracking. And they're made in panels, typically 30 foot wide by 20 foot deep box sections that are basically about 10, 15 feet long. And if you're HE sergeant, you know what I'm talking about. And then you squeeze all these together to form a concrete hull, to a concrete bridge. What we wanted to do is build bridges, build offshore wind hulls, just like we build bridges, because we know how to do that. Okay, and this way we can use an existing industry to do that in Maine. So this is a 1:8 scale version of our floating concrete hull that we built back in 2013. It's 1/8 the full size, so when you look at the people next to it, it's still a pretty big size, being at a 1:8 scale. What you see in red is under the water, what you see in yellow is above the water. So the red to yellow line is the water line. And this is, how many of you have sailed a catamaran? Okay, I used to sail when I was in college, but just a couple of weeks ago I broke down and bought a catamaran. I used one. Okay, it's a Hobie Cat, a 16 foot. Have you sailed those? I haven't sailed it yet. I just bought it, but yeah, I got a really good deal on it because the guy wanted to get rid of it. So, but a catamaran has 2 hulls, right? And how do you make a catamaran more stable? What do you do? Okay. If you put the hulls farther out, what happens? Farther apart. You become more stable. If you make the hulls larger, what happens? You also become more stable. So, so this is not a catamaran, it's a trimaran. So it has 3 hulls on it. Okay, and you can see them. Here's one, here's 2, and there's one behind that you can't see. And these are basically big concrete sections full of air. Okay, it's a big concrete air can. Okay, now we all know concrete in itself doesn't float, but if you make a concrete air can, a barrel, you're going to float it, right? Steel ships float, right? Even though they're made out of steel, right? Why do they float? It's because they have contained air. They move water. So I'm going to pass this around so you can see what it looks like, what the design looks like that we've chosen after years of research. This is what we believe will get the cost down to below 10 cents a kilowatt hour when we scale it up for this electricity. So this is a to-scale version. It's a correct proportions and others of what it would look like. So this is the water level. This is the bottom of the sea. That's the water level. So I don't know if we should turn the lights on, make it easier to see here. Thank you. So water level's here. This is above the water, so what you see in yellow is above the water. What you see, what's in gray is below the water, right over here. We paint in yellow because the Coast Guard requires us to do that. So anything that's within 50 feet, 50 feet or up has to be painted yellow for navigation safety purposes. But this hull has 1, 2, and 3 hulls, right, made out of concrete, and that gives it the stability. And now how big is this? Okay, if you're building a 6 megawatt machine, which what we plan to do, a 6 megawatt machine is bigger than what we typically use on land in the US today. 6 megawatt machines have a 500-foot rotor diameter. So the rotor diameter is 1 2/3 football fields. 1 2/3 football field is the wingspan. Okay. Notice that the wingspan is bigger than the hull span. The hull actually is smaller than the wingspan of the units, right? That's what it looks. That's the correct proportions. How big is each one of these flotation columns? They're big. Again, to give us the stability. They're 30 feet in diameter and 120 feet tall. So we have essentially 3 12-story buildings made out of concrete that float this unit. Okay, this is like 3 12-story buildings. Okay, so this is big. This is very big. And under the water we have connecting beams that connect everything. So this is what the design looks like, and I'm going to pass it around so you could actually feel it and touch it. What? I'll show you. Yeah, well, I'll get to that in just a minute. Yeah, thank you. You're just a step ahead of me. Okay, all right, no problem.
Tied to the floor of the...
What's that? Yeah.
It's anchored.
Yeah?
It's anchored.
What's that?
Is it anchored?
Yes, thank you. This is anchored to the seabed using 3 mooring lines, just like you have mooring lines on a boat. So notice here there's one chain, mooring chain. This is another mooring chain. Here's a third mooring chain. There's 3 mooring chains, 1 for each one of the flotation columns. Trimaran, tri-chain. Okay, and these are catenary mooring lines. Okay, that hook up to the bottom of the sea, and the purpose of that is to keep it relatively on station. Yes, you had a question?
If the columns are 120 feet.
The columns are from the water level to the hub is 100 meters.
No, I'm looking at the submerged.
Yes, the submerged.
What's the draft? How deep?
The draft, yes. The draft dockside is only 25 feet during construction. And we tow it out to sea, and then we ballast it down, and we go down to about 55 to 60 foot draft, okay? Depending on the location and so on and so forth. So about a 60-foot draft.
Foot depth.
Water depth, correct. In that side, there's 300 feet of water. Yeah, and so then you have the mooring lines that keep it. Yeah. Now notice from the bottom of each unit, you see this black cable. This is the electric cable that brings the power back to shore, essentially. But you bring, if you have a dozen of these, you bring all the cables together to one collection point and one cable back to shore. So you only have one cable to shore. I'll explain that in more details. But the mooring chains are just normal mooring chains. There's nothing unusual about the change. Okay.
And so what is the cable going back to shore made out of?
We have them right now. We have them between the islands and the mainland. Many of the islands, Islesboro and others, have undersea cables. We've used the cables for 30 or 40 years. There's no difference. Similar technology we've used for decades in Maine. Basically, it's a standard undersea cable. It's typically armored, and the reason it's armored is to prevent it from being, dragged and broken. So there's an armoring around the cable. Yeah, typically copper, and then with armoring around it. Yeah.
You'd be using DC for the cable.
Right now, we're using AC because it's a small project. As you go to bigger projects that are farther offshore, you want to go to DC because you reduce your losses. Yeah, high voltage DC. Yeah.
How do you determine what the blades are made out of?
The blades typically right now, I would say just about every blade made commercially in the world today is made out of fiberglass or carbon fiber. Okay.
Never used wood?
They used to make them out of wood. They don't anymore, just because the cost and it doesn't have the strength you need to make them that big. You know, back in the old days when you had smaller turbines, it was okay to make them out of wood. You could, but right now they became so big. You know, 500-foot rotor, you're not going to make it out of wood. The stresses are so high, the deflections are too high to make them out of wood today. But, okay. So this is what the unit that we put off the coast of Castine, Maine looks like. You see the unit right there. This is an aerial view of the unit. It was about 1,000 feet from shore. It was in 80 feet of water. We kept it there for a year and a half, and we had 60 sensors on the hull to figure out how it's moving with the waves and the winds, how much stress it's seeing in the mooring lines and anchors, and compare that to our numerical models. And this is how we towed it out to sea. So this is we worked with Maine Maritime Academy, and we used their tugboat to tow it out, and that's what she looks like being taken out. So we prefabricated the entire hull dockside. So the concrete, the tower, the turbines, actually we made them in our lab. We made it in our lab in sections. Took it down to from Orono to Brewer on 3 trucks, and assembled it all in Brewer on 3 trucks, and then put the tower and turbine on, and lifted the whole unit, placed it in the Penobscot River, and towed it out to Castine. It took about 12 hours to get to Castine. When we were down there, we already had the mooring lines pre-installed with a buoy on them, just like you would have on a boat, and we attached those mooring lines. We already had a pre-installed cable that brought the power to shore, to the central main power grid in there, and then and we had 60 sensors. It was like a floating lab to figure out how it works in the water, so to see if our models really work. Now, what's really significant about this and different from what Europe's doing, Europe has been building offshore wind farms long before we started doing it in the US. They built the first farm in 1991. Anyone seen the offshore wind farms in Europe? No, okay. If you have a chance, Germany, if you have a chance to go to Denmark, if you have a chance to go to the UK, you'll see them all over the place. But typically the way they build their turbines, they build them fixed to the seabed. So they have about 20-foot diameter steel piles. They pound into the seabed, into the mud, 50, 60 feet in the mud. And then they come in and erect the towers and turbines with a jack-up barge. It's very expensive, because anytime you have to mobilize these jack-up barges, they're very expensive. $200,000 to $300,000 a day for these barges. Very, very expensive to do. So rather than try to do all that out there, we're prefabricating everything dockside and towing them out to sea. So we don't need the heavy cranes offshore. We don't need to mobilize these very expensive equipment to go. And I would like to show you a little video here. This video was from December 2013. We had a storm called Storm Electra. It was a snowstorm on December 15th, and it's an example of the many storms our 1 to 8 scale saw at the time. So we'll turn the lights off just so you could see this a little bit better. So this unit saw the storm, and you can see the snow going across here, blowing across the unit, and you can see the white caps. This was equivalent to a 50-year wave environment relative to the size of that unit. And notice in a 50-year storm and all that wind, is that moving at all? You can't see it. You can't see any movement in it. And that's really the essence of this design. How do we build something extremely stable that will move very little out there in the ocean? We had another storm that was 500 years. It moved off vertical by 5.9 degrees, or 5.6 degrees. Yeah. So that's in a 500-year storm. That's how stable the hull is. Okay. So when you see the perfect storm we're all seeing in the movie, the perfect storm, the movie, is nothing compared to the storms that we've tested these against in our lab and before. So this will easily, at least is designed to last 500 years.
When this scales up, you have that much more power area. Is it going to, you think the model is as stable as the scale?
Yeah, that's exactly why we did these tests. So when we did these tests, we did the scaling physics correctly, because you can do a test if the physics are right, then are wrong, then you don't really haven't done anything. So the whole purpose of the experiment was to get the physics right. So this unit, the 1 to 8 scale, moves in the water in the same way as the bigger unit will move in the water as well. And that's the years of physics work that we actually had to do to develop to prove that it actually does work. This is an example of a storm. You can see how one of the flotation columns completely covered with water. You remember I said it's about 40 to 45 foot, 40 to 45 feet above the water, so it's completely covered in this case. This happens to be a 500-year storm. In this case, the heel angle was less than 7 degrees, and the accelerations of the hub at the nacelle level were less than 0.2 Gs in that storm, which is very important to us. So where do we go next? And where do we go next? As I said, we've received actually 2 grants from the DOE in May. One is about $40 million, the other one is $3.7 million to help cost share the construction of a demonstration project. Essentially the bigger version of this hull off the coast of Maine. We're looking at 2 6-megawatt turbines, about 2.5 miles south of Monhegan Island. The goal is to build it in 2018 and 19 and have it operational in 2019. 2 units, as you see right there. And this is Monhegan. It's about 14 miles from shore, depending on where you come from shore. The 2 test turbines are 2.5 miles south of Monhegan Island, and that's what they would look like, looking from the turbine up at Monhegan. Okay. And so this is another experiment, and we've got a lot of companies working with us and in Maine to make it work. The question is, how are we going to build it, right? That was one of the questions. Where are we going to build it? Okay, we're going to actually assemble it at Searsport. Okay, but before we assemble it at Searsport, we're going to make the base of the hull in an existing concrete facility in Hamden, Maine. There's a facility in Hamden, Maine that's a concrete plant already. We're going to actually make the base of the hulls, this base right here that you see. It looks like a starfish. That's a 20-foot deep, high starfish. Okay, it looks like that. It's 20 feet high. We're going to make that in Hamden at Hughes Brothers concrete plant. If you've been with H.E. Sargent, you've been there a few times, okay? And that facility is right on the river. It's an industrial facility. We're going to build the hulls there. We're going to move them to the Penobscot River and tow the base of the hull down the Penobscot. Okay, that's 20 feet, and it's going to have about an 8-foot draft, and there's enough draft to take it down the Penobscot River at high tide. And then when we get down there to Searsport, that will arrive at Searsport, what you're seeing right there. So, and then at Searsport, we're going to continue assembling the unit. So at Searsport, we're going to add the flotation columns to the base. We're going to basically submerge the base until it sits on the sea floor, and then we're going to stack the cans. I'm sorry. We're going to stack these cans, if you wish. They're about 12 feet high cans, 13 feet in diameter. We're going to make them also in Hamden and bring them down river on a barge. We're going to stack them on the base and post-tension them vertically together, just like you do on a bridge. Squeeze them all together, and then we're going to the tower and the turbine will come also in pieces. The tower comes in three pieces, and the turbine, the blades will be the turbine and the blades will be lifted and assembled, and then we're going to deballast the unit and then tow it out. Okay. And then we tow it out, and we're going to reballast it when it gets down there, so that's the plan right now, if it all works together. So where are we heading with this? What's the end game? If you recall, electricity is not the problem for Maine families. You remember how much does it cost for electricity? About $1,000 a year. What was the problem? Heating oil and gasoline. So what's the best way? What's one of the most efficient ways to heat the homes if we have lots of electricity? Heat pumps. Yeah, heat pumps. Whether geophysical, geothermal heat pumps or air-to-air heat pumps. If you had good price electricity and heat pumps, then you can reduce your energy costs. You don't have to pay $4,000 a year or $5,000 to heat the home. And the reason for that is heat pumps don't really generate, as you know, don't actually create the BTUs. Heat pumps move the BTUs from the outside of the house to the inside of the house, whether it's BTUs from the ground to the house or BTUs from the air to the house. So you use electricity just to move the BTUs over. You're not creating the BTUs. So it's a very efficient way to do that. So in the long run, we can use heat pumps and better weatherize our homes and offshore wind to basically to run the heat pumps. The other piece we talked about earlier is the problem that Maine family has are transportation. Right? Gasoline, $5,000 for the cars. How many of you have looked at electrical vehicles? Okay. When I give a talk to younger people, in high school, and I say, how many of you would buy electric vehicle in your lifetime? Okay, I could have 500 to 1,000 students in a room. Guess how many people raise their hand?
Not very.
Very few.
Everybody.
Oh,
Everybody.
yeah.
Everybody raises their hand. Everybody. Okay. We have a generational gap in terms of where the next generation is going, folks. It's a completely different mindset. Okay, where these young people are going. So now let's think about this. If we had offshore wind farms that produce enough electricity to charge our cars, now how often do you use your car? 1 to 2 hours out of what? Out of 24 is the average use of a car in the U.S. 1 to 2 hours out of 24. The other 22 hours, it's just sitting there. It's either sitting at home or sitting at work. And then if you can plug it into the grid and charge it, okay, you already pay for the battery, right? The battery already exists. It becomes a storage medium for wind. So wind is intermittent, yes, we all know that. There's no surprise there. But if you can actually store the electricity in the battery of the cars that's already paid for. And if you did that, you can have thousands and thousands, tens of thousands of these batteries across the state that can actually become a place to store the energy. And then, to give you a sense, right, in my lab, we installed electrical plug-in vehicles. And then you have a prime seat, okay, right near the front door if you buy one of those cars, right? So, and then people are buying those cars. And then they come in, they plug in the morning, and then they drive back home, and they haven't used 1 ounce of oil, okay?
Have you modeled a tariff for the homeowner owning a vehicle that is used to store grid power?
Yes, you're again one step ahead of me. So I'll go ahead and tell you what's really important. A number of years ago, the federal government put a think tank together. These are some of the top thinkers in the energy business in the United States, and asked them, what is the best way, what is the best method we have to deal with the intermittency of renewables? That's intermittency of wind, intermittency of solar, and so on and so forth. Guess what the best answer, number one answer came up? Electric vehicles, electric cars. Okay, because the battery is paid for, you don't have to go buy it. Okay, you already paid for the electric vehicle, you paid for that battery. Now imagine here, we're talking 20 years down the road or 30 years down the road, where most of us, or many of us, half of us have electric vehicles. And they're all 22 out of 24 hours, they're plugged into the wall somewhere. Those become a place you can store the energy. So when you have a lot of offshore wind blowing out there, you're not using it, you can store it in the cars. And then when you don't have enough energy, guess what? You can sell the energy back to the grid. Okay, it's called V2G, vehicle to grid technology, or grid to vehicle technology. So it's feasible, and people are doing that. We're working with the University of Delaware, and they already have a vehicle to grid ongoing program where people actually make money by selling electricity back to the grid, which is what you just said. So let's think about growing that to a scale of a state, growing that to a scale of a region, growing that to a scale of a country. All of a sudden, we've got this huge distributed battery system that's already paid for. Okay, and every car would have its own, IP address, just like your phone, your cell phone has an IP address, your computer connection at home has an IP address, and we know exactly the utility can ask the car to put electricity back on the grid if they have a big load, and if they don't have enough places for electricity to go, they'll store it back on your car. So it's a very simple way to address these issues. So we imagine in the 2020s or 2030s, we're going to try to put a plan together to build offshore wind farms beyond the horizon, over 20 miles offshore, and then use those to heat homes and fill up cars. And if we did that, we have a real opportunity here to reduce our costs in the long run and stabilize our electricity costs. That's the plan that we're moving in that direction. Yes?
If the thought pattern that for every reaction there is an equal and opposite reaction, if that's accurate.
That's the very first thing we teach our students in statics classes in freshman year. Okay. Yes.
What are the impacts that you guys are considering with the turbines? And also, you mentioned geothermal. What are the impacts that folks are considering with the geothermal?
Yeah. Very, very good questions. Excellent questions. I think you've asked a question that would take a lot of thought. But let me summarize here what we're doing. You ask, what is the impact of the turbines? everything we do as humans in the earth is going to have an impact on our environment. There's no question about it. So when you put these turbines out there, you have to worry about the birds, you have to worry about the bats, you have to worry about the fish, you have to worry about the mammals in the water. You have to worry about other people who want to use the same environment, fishermen and others that want to use the same environment. You have to worry about recreational uses of the space and so on and so forth. So all of those are important issues. And we're studying these issues. We haven't figured out where we're going to put in yet these larger farms. So that's something that needs to be studied, and people have to work together to get to those solutions. Other states...
You're using 12 turbines in a grid.
Yeah, you can, you know, what they're doing right now in Europe right now, they're building much larger farms. They're building farms that are at, near 500 megawatt in size. They might have 83 6-megawatt turbines, okay, typically placed a mile apart in both directions. So if you want to build a 500 megawatt farm, getting to the size of near nuclear power size, you need 83 turbines. They'll take up a space of about 4 miles by 4 miles, roughly, out in the environment. To put things in perspective, you've asked a very important question. The question is, what do we need in Maine? How much electricity do we need to heat every home and fill up every car, should we choose in the next 20, 30, 40 years to move to offshore wind, to do that? What we figured is you need about 5 gigawatts of offshore wind. If we build 5 gigawatts of offshore wind over 20 miles offshore, beyond the horizon, that's enough to fill up every car in the future with electricity, and enough to heat every home in Maine. So you remember we said how many gigawatts do we have out there off the coast of Maine? 156. Let's do the math. What's 5 divided by 156?
3%.
3%. So do you think we can all agree, by doing a lot of studies, that we can find 3% of that real estate off the coast of Maine, over 20 miles, where we think it's okay to put a farm? Do you think it's possible? Okay, then we're going to agree on 3%. Okay, and now to put that in perspective, they've done that in Europe already. They've been doing this since 1991. Today in Europe, they have about 13 to 14,000 megawatts of offshore wind installed. Thousands of turbines have been installed. Okay, already. So they've figured out how to do it in Europe. Okay, they've already figured out where they would do that. The leaders in Europe are the UK, and Denmark and Germany. And I would suggest, if you're interested, to go see what they've done. So they've done a lot of environmental studies. What is the impact? What are the impacts of these farms on the birds, on the bats, on the fish under the sea? They've done all kinds of studies around that. And I would recommend you go to the EWIA, European Wind Energy Association website. There's all kinds of studies on that, and you can read them for yourself. But what they found in general is that the impact is very minimal. What typically happens is they actually have video. They have radar studies of migratory birds coming into the farms, and the birds fan out around the farms. Okay, that's what they typically would do, and those are actually, you can see, very interesting tracks of the birds doing that. But it's important for us. We don't have the same bird species they do out there. Will they do the same thing or not? Where do migratory birds travel in the Gulf of Maine? How do we avoid them with these turbines? These are very important questions, and we should not go out there and build farms before we understand these questions. And so we're working with fish biologists, we're working with bird biologists and others who are actually trying to understand these questions. Do we have all the answers? No, we don't. Do we know where all the migratory birds travel? No, we don't, off the Gulf of Maine. So we have to really better understand these questions. And there are other ways to mitigate some of these problems. If, for example, we have bigger farms in the future and we know migratory birds might come in, what we could do is we could put sensors, radars, to find out when the birds are coming and shut the turbines down when they pass over. So these are things that can be done and to mitigate, if you wish, some of these impacts. In terms of fish life, actually, because oftentimes offshore wind farms are not fished, they become like sanctuaries for marine life, and in Europe they've seen in some cases an increase in marine life because of these became fish sanctuaries, and then because of that more birds came in to eat the fish. So it's kind of interesting. But there's been, again, they have a longer history than we do. They've done it since 1991, so we have a lot to learn from them, and hopefully learn from their mistakes and do it better as we do it here in the U.S. So that's in terms of the impact. The other impacts, of course, the impacts on you said you asked about the impact of air-to-air heat pumps and other things. No, these impacts are very minimal. We don't see what an air-to-air heat pump is. It's almost like an air conditioner unit that you put. It's a reverse air conditioner that you put on the wall. You put outside the house, and then those you can buy today. You can put them out there, and they're powered by electricity. So they're very green because they don't use a lot of electricity to bring BTUs into the house. So the impacts are very minimal because these are individual units placed in homes. Now geothermal is a whole other thing. We're not saying geothermal. We're talking about not geysers and other. That's not what we're talking about here. We're talking about taking the heat from the earth, the calories from the earth, or the BTUs from the earth, and moving them into the house using heat pumps as well. So you have, you would run liquid in the earth, pipes buried in the ground, and you would use pump that energy back into a house, and that's different from the typical geothermal we're talking about. That's more of it's a heat pump that utilizes the ground source as a source of BTUs. Okay. And that's what we're talking about. And people have been doing that, and their impact, particularly in large developments, if you have a large development, say a big development somewhere, you might have 50 homes or 100 homes. What people try to do and have done in Europe is actually build one big facility to heat all the homes, rather than build a facility for each house to reduce the impact. But the impacts are minimal if it's done right. There's very little impact there. So. Air-to-air heat pumps, so I don't see a big issue. The issue I see is really properly locating these farms to ensure that we protect the birds and the bats and the wildlife. We have a lot more to learn there. So, yes.
Are any of these European countries learning from you in the floating concept, and are they moving in your direction?
Yes, you've asked a very good question. What people in Europe are learning is that it's potentially less expensive to build it using floating wind turbines. So we have a number of companies from Europe have been up here, interested in what we're doing, and one of them has become a major investor to the project. Actually, been in the news. The company is called DCNS out of France. It's a big company, 12,000 employees, and they build ships for the French Navy and navies around the world. And they want to invest in this technology as well. So yes, there's been a lot of interest from Europe as well. And certainly as soon as we build these 2 units, you will see the interest also increase as well. But yes, there's been interest to do that. Yeah. This is, by the way, a large storm that came in, 22.6 meter maximum wave, so about 70-foot maximum wave in here. Not every wave is maximum wave, but if you see how little the unit is moving in a 70-foot wave, relative to the size of the unit, you'll see the flotation columns getting covered by water because of the waves. So, but anyway, yes, please.
How loud is it?
Loud. When you put them 20 miles offshore, you're not going to hear them, certainly. And then, so what we've done is every turbine has a different noise profile or a sound profile, and each manufacturer has characterized its sound profile. So what you need to do is, when you're going to locate them, you want to put them far enough so it does not really disturb populations around it. That's what you try to do. But our goal is to put these, as we said, in the long run, 20 miles offshore. At that point in time, it's a non-issue. Nobody's going to hear them.
So it's hard to measure the sound?
The sound doesn't travel that much, basically. The sound that it will produce doesn't travel 20 miles. Actually, it travels less than about 2.5 to 3 miles. What we've done some studies in Monhegan, for example, off Monhegan, where we've actually placed sensors throughout Monhegan Island to see what the sound of the waves and ambient sound is. Even though we're 2.5 miles south of Monhegan Island, the sound from the turbines to Monhegan is less than the sound of the waves and the ambient noise that you would hear in Monhegan anyway. So when you're 20 miles offshore, you're not going to hear anything, essentially. Yeah.
What about the sound underwater for whales?
Very, very good question. And the sounds and the noise that these things would make are a lot less than a ship would make, the ship propeller would make, for example, and so forth. But they have not seen any issues with that in Europe. What they've seen issues with is actually installing these units. When they put them in, as I said, they're using 20-foot diameter piles, and they pound these into the seabed. When you pound these into the seabed, you're using big impact hammers to pound. Think about it, 20-foot diameter steel pile, 2.5 inch thick walls, pounding that 80 feet or 60 feet or 40 feet into the mud. the noise that you create is so high you can actually kill fish because of the noise propagation. So what they do is, and that's required now, is they put blankets, these are noise blankets around them, basically air-filled noise blankets, to contain the noise as they pound these piles in. But once you do that, once you've done the construction operations, the actual operation of the turbines they haven't seen any issues with mammals and so forth. What we've done to try to understand better what happens is we spend a couple of years measuring, putting sensors on fish that live in the Monhegan area. We actually put sensors on fish and tracked where they go. And so now we have a good understanding where the fish actually move around and what they do around Monhegan Island, how many fish are out there. We've put acoustic sensors under the water as well to see if there's any other activity we could hear. And we've done that above the water as well to measure the environment. So we've really mapped the environment around the turbine very well. And the reason for that is when we bring the turbines in, we're going to continue to do the same thing and see, okay, have we really impacted the environment? Are there less fish now or not? Are they still traveling the same way or not? So we'll learn that as we go along. Again, it's only 2 turbines, and the only way we're going to really understand the impact is if we study it on a small scale. And that's really what we're trying to do with this effort, is study it at a small scale so we don't make mistakes on a larger scale. Yes. Yes, please.
A few minutes ago you mentioned that marine life could actually increase in the areas around turbines. I assume that you mean the European.
Correct. Yeah, we don't have any experience in the U.S. You're right. Yeah.
But how would you explain that? How could
I would refer you to the EWIA, European Wind Energy Association website to read. There's a lot of scientific reports that were written independently as part of these programs. So we didn't write them ourselves, but you can go read them. But the idea is actually fairly simple. Oftentimes, when you have a big farm like this, okay, you might have 30, 40, 50 turbines in there, and then fishing is oftentimes not allowed in those areas. So, and those areas might be a 3 mile by 3 mile or 4 mile by 4 mile area where there's no fishing. And you have these kind of big artificial reefs, which is the foundation of these turbines. So essentially you've created a habitat for fish where they're not fished, so basically it's a protection habitat. It's almost like a protection area that you've actually built. And you've provided artificial reefs for marine life to grow on and then fish to feed on and so on and so forth. So that's the way to explain it in a kind of a very simplistic way, but I would recommend that you look at some of these reports that are out there.
What about the electromagnetic frequencies from the transmission lines?
Transmission lines, right. There's been a lot of studies done on that, on the EMF issues with these lines, and they haven't seen any impact that I know of, certainly, but again, there's a number of reports that you could read on that. But these undersea cables are no different than the ones we're using already in Maine. The islands off the coast of Maine have been connected to the mainland. That's how you power the islands, many of the islands, using the same cables. We've been doing this for decades in the state of Maine. So there's no different than, we're not creating any new types of cables here or doing anything different.
Well, they're much longer.
No, they're the same. It depends on where the farm is, right? So yeah, it could be, if the farm is 20 miles offshore, it'd be a 20-mile cable. Yeah.
And they're armored.
They're armored, yeah. And typically what we do is we, whenever you can, of course, and you can't do that in the Gulf of Maine all the time, you want to bury the cables in the seabed. Typically they're buried, and if there's mud, they're buried about 4 or 5 feet or 6 feet into the mud. And if there's no mud, as we have a lot of situations in the Gulf of Maine, you berm it. You put a berm over the cable. So, yeah. But again, this is a very important questions you're asking. Again, I would refer you to all the work that Europe has done. They have thousands of turbines since 1991. They've done all kinds of independent studies of these, commissioned by different governments, and they've all coming to those same conclusions. So I would say, please go ahead and read up on that using the EWIA website. They will refer you to a lot of studies. Yeah.
I have run high voltage submarine cables.
Oh, you have?
And I've also installed large fish farms. In the case of the cables, they are jacketed. The insulation jacket doesn't allow for EMF to occur outside the cable. I mean, if it did, eventually you'd have a short right there. So the cables that I've run, we test them before we turn them on to make sure that they are 100% insulated out to wherever they're headed to. and we come back every 10 years and test them to make sure that they're still holding current the way they were designed to hold. So I don't see any problem with the transfer of electricity from where it's generated to the mainland. And in terms of the fish farms that I've installed, every one of them, the biota has increased under that farm, but for a number of reasons. But the one you mentioned, I find to be a primary reason, which is the habitat change.
Exactly.
With that, most of the bottom, and I'd say 90-some% of the bottom of all the water that we see is a very soft bottom, and these structures come along and they rely on a holdfast. They rely on something that's basically concrete, and that provides a habitat for critters, in a sense an atoll. So there's an enormous migration of animals to this.
Thank you for the input. That's very helpful. Thank you. Yes, please.
Several years ago, there was a lot of controversy about the governor's decision to reopen the bidding for the offshore experimental project. And I'm sort of curious, and as a result, at least as I've read, Massachusetts and particularly Rhode Island now have offshore wind projects that are underway with European companies. And I'm just sort of curious what your take is. Maybe it's 3 years down the road now in terms of that decision. Has that adversely impacted us in Maine in terms of offshore wind development, or was that advantageous because we had held back and we've done experimental work and maybe we'll come forward with something that is more cost effective? How do you understand that?
Yeah, I think in general we find ourselves in a good place right now. We're the only state in the country with a floating project that's going to go forward. So in many ways Maine is still leading the charge in floating wind technologies. It allowed us to develop our own concrete hull technology, which can be actually produced in Maine because we mine concrete in Maine here, cement in Maine, right here in Thomaston. So I think we have a good project. I think I'm optimistic of where we are today and where we're heading in terms of Maine. Yes, other states have projects currently, and the first offshore wind farm in the U.S., commercial farm, is going up as we speak in Rhode Island.
Yeah, right.
And actually, if you just type Deepwater Wind, that's the company that's building it. They're actually putting the turbines as we speak up, and they're turning them on right now. And there's 5-6 megawatt machines, the same machines that we'd be using, but theirs are fixed to the bottom. Ours, yes, they're fixed. Yeah, no, we're the only ones that can. We'll be. Maine will lead the floating world, if you wish, and if we can make this work. So I think Maine is still in a very good shape to move forward. And yeah. Yes, please.
How far offshore do you think it's feasible to put these in when you're thinking about the length of cables and that sort of thing? Obviously, the farther offshore, you get slightly improvement in the wind speeds, especially when the wind's blowing from the land.
Yeah. Actually, very good questions, and it's at the end of the day, there's a lot of pieces that come to that decision. The cable, of course, the cable length is a piece. The bigger the cable, the more expensive you're going to have a farm. But you might get better winds when you go out there. So that can balance out, as you said. Yeah, but the big issue also are how deep the water is. Okay, if you're off the coast of California and you get to 3,000 feet or 4,000 feet of water, then it becomes very costly to put the mooring lines in and so forth. So you've got.
What is the problem with the deep water?
You use larger mooring chains, so basically it becomes more expensive. So it's a balancing act in terms of where it makes sense. In terms of how far can you do it in Europe, they've done fixed bottom farms close to 90 kilometers offshore. Okay, so very big farm. So it's a function really of the environment, the cost, the wind speed. A lot of pieces come into it, but they've been done at 90 kilometers. So it's. Yes.
Just a question about nanotechnology and future implications of nanotechnology to this in terms of coming up, with turbines and things, strong materials, very lightweight. Where is that headed?
Very good questions. Actually, the bigger blades that we're, when you go to 6 megawatt machines, the rotor diameter is 500 feet. Actually, there's a machine today. The biggest offshore wind turbine in the world today is made by Vestas and Mitsubishi. It's operating now in Europe. They just put them up there last year. 8 megawatts. Okay, and it has a rotor diameter of 2 football fields. Okay. When you get to large turbines like that, large blades like that, you need more exotic, better materials to hold up and in the environment, carry the stresses over longer spans. So people go to carbon fiber, at least some partially carbon fiber in the blades. We're doing research at the university in enhancing the resins using nanofibers and nanoparticles. We're doing a lot of work on cellulose nanofibers, actually breaking down the tree into its nanoparticles and then putting those particles back into the resin to make better resins. So there's a lot of opportunities. Also, you can make concrete better potentially with nanofibers, so it doesn't, it'll last longer and so forth. So all of those are real opportunities, of course, but they're years in the making now. We're still in the developmental stages of developing these technologies. Yeah.
Thank you so much. That was so interesting.
You're welcome. It's really been a great pleasure, and you're welcome to all. If you want to come and have a tour of the lab and see things firsthand, you're certainly welcome to come up to Orono and see that. And
so if we were to do that, do you get a group together? Or
yeah. If you get a group together and
what's
just
a good size group?
really whatever you want. So it's we've accommodated anywhere from probably 20 people to 50 or 60. But if it's in that 20 to 30 person range, it's a lot more interactive. So it'll be better that way. So and it's nothing like seeing it firsthand. You get to appreciate what's happening. There's a lot going on in the lab actually. In the next 2 to 3 weeks, we'll be testing our final 150 scale floating turbine in our wave wind basin. So it'd be really neat to see. We'll be putting in the 500-year storms on it and so forth. So it'd be neat to see that. But
thank you so much.
My pleasure. Yeah, my pleasure. Yeah. Thank you.
Thank you so much.
You're welcome. It's a great pleasure to be here.